So on my clock, it's 3 p.m. So I'll wait up to 1 minute and then we will start, okay?
Mm-hmm.
Okay.
Good plan.
Sounds like a plan, yeah. People still keep coming. So, okay, well, we'll be fine.
Mm-hmm.
And maybe we will, for the main part of the webinar, we will switch off the cameras, and and we can switch them on because it's more gives more impression of the interactivity. So we will switch them on for Q&A.
Mm-hmm.
So we will
Good
come back.
plan.
Hopefully we will remember. So I think we can start the webinar. It's yeah. So I think it's time, definitely. So hopefully you can see my screen and hear me. So
Yes.
I think we can start. Hello everyone. This is Luboš Pirkl from CFD Support, and I would like to welcome you to the webinar where we would like to show you a simulation workflow of Francis Turbine, especially CFD setup, simulation, and post-processing, and also a little bit of FEA, FSI, and optimization. And yeah, so it's webinar number 71, and we would like to have fun. So the webinar is being recorded, and the recording will be later made publicly available on our YouTube channel. So anyone can look at it later. And yeah, there will be 3 parts in the webinar. I will give a general introduction to about the software and general principles and our philosophy. Then my colleague Radek Máca. By the way, hello Radek, can you hear us?
Yeah, hello Luboš, and hello to the audience. Yeah, I can hear you, I can see you, so everything seems to be working perfectly.
That's great. That's great. Yep. So pleasure to have you here. So let's do another nice job together. So first part, quick introduction. Second part, Radek will show a hands-on session about the principles, how the workflow is constructed, what are the inputs, what's the setup process, what's the simulation process, and what's the post-processing principles. And after that, we will do our best to answer all your questions. It's a very important part because we do the webinar for you, for the audience. So I would like to ask everyone to feel free to ask your questions, and we will do our best to answer them. We will answer all the questions. The most relevant and representative questions will be answered right away here in the webinar, and the rest of the questions, some specific questions or those we don't know the answer right away, we will answer later via email, but you can be sure that all the questions will be answered. And I hope I can go ahead. I would like to invite you for the next webinars. So for example, in 2 weeks on October 24, we will specifically deal with simulation-driven optimization for turbo machinery. So the next webinar will be specifically about simulation-driven optimization. So I would like to invite you for the next webinar. So we can mention some simulation optimization details still today, but the next webinar will be specifically dedicated to optimization. So feel free to show up. And yeah, then the big day is on November 9. We will release the new TCAE version 23.10. We have spent enormous time and effort to resolve a lot of fixes and also of course new capabilities and etc. So the new version is coming on November 9, and we will introduce it to publicly in the webinar in 1 month. So basically it's in 30 days. Yeah, the next webinar is about centrifugal pump. I'm sorry, centrifugal pump, CFD, FEA, FSI, and optimization on November 21st, 21. And then the webinar 75 is on external aerodynamics. And the last webinar of this year will be dedicated to Kaplan hydro turbine, similar to today's webinar. Okay, so those are a couple of webinars still to come this year. Looking forward to see you there. And okay, I'll go, I would say, very quickly through the introduction phase of this webinar. So CFD support, the Czech Republic located company in Prague. We deal in general with simulations. Specifically, we deal with CFD, FEA, and FSI, and specifically we deal with optimization, simulation-driven optimization, and acoustics. All these simulations are our best, I would say. And first of all, we are developer or vendor of simulation environment called TCAE. And this is what today's webinar about. But if you don't use TCAE still, no, don't worry about that, because we will show general principles, and these principles are valid in a very finite volume software available in the market. So it's not necessarily a condition to use it this way in TCAE, but the principles are valid or everywhere across standard simulation software pieces. And by the way, Radek, I suggest we will switch the cameras, right? Switch the cameras off. Yeah, because
Good.
It will.
Yeah. I didn't want to interrupt you because I didn't find the white space to interrupt you.
About me.
Yeah.
No worries. Let's switch them off. And I believe it will give the audience a better aspect ratio of the presentation. So we will come back. Hopefully, we will come back for Q&A session and on. We will finish with cameras on again. But now I believe it's better when we present something like this. It's when you see the whole picture. Okay, so what's on the table? It's TCAE. It's our software. We believe it's pretty unique for several reasons. It has multiple, it has several software modules for mesh creation, for CFD, FEA, for acoustics, for optimization, and other stuff. There are a couple of reasons why to use it. We follow a couple of principles. We follow them really carefully, and we are very strict about them. So, and proud of them. So it's flexibility. So TCAE is extremely flexible, and every user can set up his or her own workflow which fits his purposes, fits his technical requirements, resources, experience, skills, time, and everything. So it's extremely flexible. You can combine TCAE, in fact, the modules you can combine them with other codes, other commercial codes, in-house codes, with other open source pieces, and it's definitely extremely flexible and fits a very existing workflow, or you can create a new one, and so it's very flexible, definitely. Standard license is unlimited, so the users can use their or her resources to the fullest. So there are no limitations on number of users, jobs, or cores, hardware installations, and or the way of usage. So it's unlimited, really useful. It's focused on turbo machinery applications and external aerodynamics. So TCAE is not software for everything. It's focused software which allows us to be accurate. So we did a lot of benchmarks in the past, and we are ready to show them and prove TCAE is really focused, accurate, flexible, and unlimited software. It can be used remotely. It can be used on PC, on laptop, on desktop computer. It can be used on the cloud. It can be used remotely. It's developed in 2 versions. It's developed for Windows. It's developed for Linux, and the workflow is exactly the same everywhere. It's based on open source, so it's very important that it's very, I would say, transparent, because the source code of all of the solvers and many physical libraries and everything is included, so the users can make sure what methods are exactly used. So it's definitely not a black box. It has open source. It's based on open source, and a lot of effort has been spent with developing it. So, for example, the CFD solver is based on OpenFOAM, and we spent more than 40 man-years of developing open source libraries to be able to solve the industrial problems. It really we really have spent a lot of time on making things applicable in the industry, and we are definitely ready to prove it. Yeah, we have a couple of unique I would say capabilities. For example, it's the acoustics. So the acoustic module can solve the acoustic properties of the flow. Then it's, I'm sorry, I skipped. Okay, yeah, then it's definitely the optimization. So specifically simulation driven optimization is really big thing that yeah, we believe it's a big shift in all the simulation workflows. And finally, our next big move is delivering a new module which is called T-Base. We did not make it to deliver it this year, but we will definitely deliver it early next year. So in the next version, hopefully in March or something like that, next year we will deliver this new module which will allow users to create their own specific knowledge databases, which allow them using machine learning and AI to suggest to get the surrogate models and allow them to get the results in quality of simulation in seconds rather than in days. So it will be a really big thing, and we are looking forward to it. We already have something, and it's really good. Okay. Anyway, let's move to the hands-on session. So I would like ask Radek to show how to let's say set up and simulate and post-process the Francis turbine, and let's see from there. So
Perfect. So
okay, I will hand over the presentation to you.
Okay, show my screen. So I hope you can see my screen now. You can hear me.
Yes, we can see it.
Perfect. So I will continue. Thank you, Luboš, for the introduction, and I will smoothly continue to the hands-on session. So today we will go through the Francis turbine case study setup. All the case studies can be found on our web pages. If you go to the case study section, then you can see the list of all the benchmarks or the tutorial cases we did in the past, and one of them is the Francis turbine. So you can directly look at the detailed description of the model, how it is connected, or how the real model exists to this Francis turbine, etc. You can download the data to it to try it on your site if you would like to go for the trial license, for example, and you can check all the resulting data. So I have already downloaded the case here on my disk, and basically what you need at the beginning, if you start from a scratch, you need the geometry data. Yeah, so you need to have the watertight geometry, so watertight, waterproof geometry, which defines your flow domain. And if you don't have any mesh engine and you would like to do the whole workflow in the GUI, in the TCE, then you need to have the set of STLs which describe each part of the geometry, and as a whole it builds the whole computational domain basically. So at the very beginning, what you need is kind of set of STLs which defines your whole geometry. So if I open everything, so this is a standard paraview which can be, for example, used for STL view, and then if you want to start setting up the simulation, then you will directly go to the TCAE. So we have both the surface geometries, and we have also here the solid for the FEA analysis. So maybe if we have time, we'll have a look on the setup, and maybe we can keep it for the next webinars. So this is only what you need, except the other computational parameters which you need to set in the graphical user interface. So now I will go into the program. So I can just double click the icon, then the GUI appears to me, and now I can directly start setting up the geometry from scratch. Well, because just to speed up the simulation, so maybe I will just show you an example of a simple part of the geometry. So for example, if you directly open the tutorial, which I have already preset here, so if I directly open it, then you can see everything preset. So it is ready to run tutorial. All the parts of the workflows is set, and you can just go through it, and basically you can click run all button, and all the parts of the workflow will be run immediately. Yeah, so this geometry consists of 3 components. I won't be speaking into much detail, but we always build the geometry from components, which is the part which has some kind of internal meaning for the whole machine. Typically, we have parts which includes volutes, sometimes also the vane gates or the guide vanes, or we have a component just for the rotor part and for the draft tube part. And as an example of what we can do from scratch, just to see you how to work with the empty project and how to start building the whole workflow, is that I open the new environment, which I have here. Now I will create an empty project. So now the new project is created. I will store it somewhere to my disk. So I will go, for example, to my webinars directory in today's webinar, and for example, I will name it as test case. So now I have the empty project saved on my disk, and now for example, because I would like to start with mesh definition and computational mesh creation, so I will click on the T-mesh module, and now a new item appears here, and I can start setting up the geometry. So as a quick example, what I can show you is to for example just model the draft tube, which is the simplest part of the whole geometry. So let's say I will have just one component, and I would like to define or compute the flow through the draft tube itself. So now what I can do is to import new surface geometry. So I will click here, then I will locate the STLs which builds the draft tube. So I have here this draft tube wall, then I have the interface from the rotor, so it is this one, and I need the outflow. So I will load just these 3 STLs, which builds my draft tube section. What I need to do additionally, so here's some kind of rotational reference frame, which is made for application with rotation. So here I have no rotation, I have here no transformation needed. For example, some kind of sections built by the part of the some kind of full wheel geometry, so I don't need to play with this, but for the turbo machinery application, we'll just define the axis of rotation, which is pretty simple. And what I would like to do is just to set the part of the geometry. So here I have a draft tube. So first, the default type is the wall, which is okay. So draft tube is a rigid wall. Interface throttle will be here just the inlet, a physical inlet into the domain, and outflow will be the outlet. So this is the part of setting up the types of the boundaries from the CFD point of view. And now I need to define the mesh parameters. So the meshing is done by the SnappyX mesh, which works, which starts from a kind of initial mesh, which is a hexahedral shaped mesh, which consists of splitting in each direction. So I can give the sizing of the largest cell. So for example, if I put, for example, 10 centimeters as a background, as a largest cell in the domain, which could be okay. And this is my initial cell size. And then if I would like to refine the mesh on the walls, for example, on the draft tube wall, I can set the level of refinement. Yeah, so in this way. And if I would like to add the boundary layers, I will set how many boundary layers I would like to add. So let's, as an example, I will add 3. I would like to generate the 3 boundary layers. So this was the very basic mesh parameters. And the last thing I really need to set up is the internal point, because we need to, because it's starting from this initial background mesh, and you need to distinguish which part of the meshing at the end of the meshing process will be kept inside of your object or outside, for example, for cases of the external aerodynamics. So here we are simulating the internal flow. So we need to place this point, which is also visualized in this render view. So I can just use the visualization by a sphere just to see where my point is, and I need to just put it somewhere inside. It doesn't matter where you put it inside your component. Okay, and let's say this is kind of compulsory setup which needs to be done, and now I will try to generate the mesh. To speed up the mesh generation, I can set number of processor to be used for the parallelization, and my computer has 10 cores, so I can use up to 10 cores for the mesh generation and also for the other CFD simulation or FEA simulation. So now I will save the project, and I can click Run All, which runs the all workflow of the all modules which are enabled right now. So it is only the T-mesh, and I have one component, so the meshing of the component 1 is running, and within, I think, a few seconds, it's already done. The mesh is generated, and now I would like to see the topology of the mesh. So I can click this Show button. I can get rid of the input geometry, which is stored by this item CFD geometry, so I can get rid of it. And now I can visualize this CFD mesh. If I click here, surface with edges, I can see the topology. You can see kind of layer addition. You can, if you would like to see what is happening inside, so you can make a slice. You can make kind of positioning of the slice. Now you can click apply, and again show surface with edges, and you can see the topology of the mesh from the inside. So let's say, as an example, I'm satisfied with the mesh resolution, and if you would like to go quickly for the CFD setup, so we can go it also as quick as possible. So I will enable the CFD module. Now I will set very quickly the basic simulation. So I will go for the simulation type because there is no turbo machinery. So I will go for the stator type. Physics, I will switch to water. I will use fluid default, which set me some kind of default parameters for water. And I will quickly go to set up the boundary conditions. So for example, I would like to set the volumetric flow rate for 10 cubic meters per second. I will keep fixed pressure the outlet. I will keep all other values in default, which is the rigid wall for the walls. And for the initial condition, I can set some kind of initial guess. So the go flows in following the Z direction, I guess. So I will put, for example, 2 meters in minus Z direction as the initial condition. Now I click Save Project, just to be sure that I set everything what is needed to be set. I can click here check button, which shows me that project is okay. So let me try run all button, and now you can see the simulation is running. CFD residuals are showing in my view. I can, for example, add additional parameters, which is stored in the quantities item here. And if I go to the display, I can follow, for example, total pressure difference and see it, what is happening runtime. I can go for a custom range because it focused on also on the initial values. So there will be, so maximum value should be 0, I guess, and minimum, for example, 10,000. Maybe I can also by mouse, I can focus on my desired value and follow what is happening during the simulation. And basically this, roughly speaking, this is what you need for any of the application. Some, of course, the geometry is typically more complicated, so more STLs has to be set up and treated, and the mesh parameters has to be also tested carefully and set, but the principle is very the same to achieve the CFD simulation. So this was a very quick example, and if I go back to our example of Francis turbine, so I will skip the creation step by step because we will be here more than an hour, I guess. Just the basic setup. When I click everything, so if I go to the T-Mesh module and just repeat it, what was done here in this case. So here we have 3 components. So you load the STLs for each component. You assign the boundary types here for the component 2, because component 2 defines the rotor part. So you need to set the reference frame as rotating. In the rotational frames, you need to set appropriately the axis of the rotation, to follow your geometry. And basically, that's it. You go step by step, set all the mesh parameters for each part. In several loops, you will try to generate the mesh, look for the quality of the mesh, both visually or in the numbers. You can see the output messages, or in the lighter port, which you can generate after mesh generation. And step by step, you tune your simulation mesh to achieve your desired mesh quality. You can also, for example, this is the example of refinement region. So you can also refine the mesh locally using some predefined shapes. So this is, for example, the region in which you can set, for example, this is for the draft tube, where you can set, okay, all the parts which is intersected by this refinement region, by this box with the draft tube, will be refined to level 2. So then, for example, below the rotor wheel, where many recirculation areas and important flow vertices appears, so you would like to refine the mesh more, just to reveal this vertices in more detail, to have more, better accuracy in the solution. So you can play, for example, also with the refinement regions. Here's the component map. We just show you topologically how the simulation mesh is built or constructed, by the component, and which patches connects to it's connected to the next component, and so on. And in the advanced meshing options, basically all the SnapX mesh parameters are available to be changed. So for more experienced users, you can also play with these kind of parameters. If you go to the CFD, so now we are happy with the mesh, let's say, and now we are going to set up the CFD simulation. So again, all the setups works as a wizard. So if you go from up to the bottom, you don't miss anything. You don't miss any important parameters. So simply start checking the parameter from top to the bottom. So first parameter is the simulation type. As Luboš already mentioned, we always focuses the application, or we tailor the workflow to the specific application. So here we have the hydro turbine, which then gives you specific parameters which are strictly connected with the type of the simulation. So with the hydro turbine, for example, in the time management, in the physics section, you can set several points to be simulated within a single simulation. So you can evaluate different flow conditions, which results in a nice graphs, in the nice efficiency maps. So you will see the efficiency or heads or any other quantities with respect to the different flow rates or your main quantity to follow. Each number is the denotes the maximum number of iterations. So I think it's for a CFD community, it's well-known parameters. Fluid properties. In the multi-physics, you can enable some specific post-processing or some specific treatment or specific models to be enabled within your application. So for example, here we have the cavitation risk, which will give you kind of post-processing parameters, which shows you if your machine under the given condition can cavitate and kind of intensity of the cavitation. So it's kind of post-processing using specific formulas. Here what you need to set is the cavitating patches. So you will set the patches which should be evaluated for the cavitation. Low pressure and high pressure patch means for the evaluation of, for example, cavitation index, the sigma value, or net positive suction head required based of some histogram method. So we will introduce this in the webinar, in the new release webinar, into more detail, this feature. So this is, for example, one example of a new feature which we have developed to have a more insight into the hydro turbines or pump simulations. So this you fill, and then at the end, for example, maybe I can show you right directly that in the final report, you will see the section cavitation risk, which is here, and it will show you the flow rate versus cavitation risk. So it means here you can see how many percentage of the surface or of the volume is cavitating. So you can see for a higher flow rate there is some kind of cavitation, or cavitation may occur because it's the post-processing, and it somehow compare the local pressure with the saturated water pressure, and then evaluates the possibility of cavitation. Then there is a cavitation index, so specific formula to evaluate the sigma value. And again, it's based on some kind of histogram method. So based on a histogram that it just throws up the given area of the whole cavitating patches area. And based on this histogram values, it evaluates the cavitation index, or in the similar way, it evaluates the net positive suction head required, and you can directly compare to the net positive suction head available, which is evaluated from the outlet pressure value, which you set as a boundary condition. So this, for example, is the cavitation risk, which can be enabled additionally. And if we continue turbulence, I think it's clear. Rotational reference frames, here you set the speed of the rotation of the wheel. Just keep in mind and check if the direction is set properly. So you just follow the right hand rule, following the axis direction of the axis. So You can set the positive or negative direction of the wheel revolution. Inside the simulation section, you can set number of processors, again up to the number of processors you have on your machine. You can go for several types of numerics. So typically, if everything works well, and for water turbine application, we typically go for the second most accurate numerical solver which is offered. For the runtime evaluated quantities, you can play, or you can enable to enable or disable additional evaluation. So for example, you can evaluate some kind of turbulence like quantities for visualization of the vortices or the turbulence intensity of the field. You can write the average quantities because the solution even goes for the steady state. It is average over the iteration to really have a nice, robust and converged solution. In the efficiency probe, here you define the places from which the torque, power, head, and other quantities are evaluated based on what is the inlet patch for evaluation, what is the outlet patch for evaluation, and what are the torque patches for torque evaluation or power evaluation. You can define additional functions like forces evaluation if you would like to see force acting on the specific part of your domain or of your machine. You can see what is happening in the exact point within the flow domain. If you would like to speed up the simulation, you can set your target accuracy, so you can set the efficiency. Now what we have developed, what is a new feature that you can choose between the absolute tolerance. So for example, if my accuracy is, let's say, 0.1%, so I can set the absolute tolerance to the 0.001%, 0.001, which corresponds to 0.1%, and the simulation will stop if the accuracy or if the efficiency doesn't change more than this absolute value for the efficiency. You can also add different types of the convergent checks, including the power or whatever you need. The controls is connected to the numerics and the linear solvers parameters. So I can skip it for now. Within the scripting section, you can define your user-defined function, let's call it. So you can incorporate any specific treatment with the case, with the data, or whatever you need, which is not directly available in the GUI or in the parameters offered here. And from the simulation point of view, the most important part is a proper setup of the boundary conditions. So here you set inlet and outlet boundary conditions following your desired goals. So what condition you would like to follow or simulate, and based on this information you will set the boundary conditions. So typically some kind of flow and pressure combination of the boundary condition at the inlet and at the outlet. The same for the walls. You can, if you have some kind of extension just and you don't need to, you just don't want to see, or maybe I'm going into much detail, but for example, for the extension part where you would like to just extend the part and you don't care about the friction of the walls, just need to edit from some specific reason, you can go for slip wall. So it is the wall without the friction. You can play with the wall turbulence boundary conditions. So you can choose with the offered options. Within the interface conditions, you set the treatment of transferring the information from one component to the other component. There are two types, AMI, it's like frozen rotor-like application, and mixing plane, typically for for the segment geometries. So if I have only a section of the wheel and I would like to connect this section with the neighboring component, I need to apply the mixing plane approach to properly transform information from one component to the other component. Initial condition, so I think it's straightforward, and post-processing section includes some adjustment of the final report, which we can then see after the simulation. You can also play with some kind of specific visualization techniques tailored for turbomachinery applications. In the samples, you can sample some values on a specific part of the geometry for some kind of later post-processing in the external tools or in external softwares or scripts, which somehow evaluates the quantities you need. And this miscellaneous section defines some additional treatment with the data, so the storage to the CGNS format, for example, writing the surface quantities, for example, for external FEA or another post-processing, and so on. And basically, this is it. And again, to run everything, you can hit this run all button. All the parts are simulated automatically. Everything is stored in the logs, and at the end, you will see a nice report which summarizes what you have said, details about the mesh, about the setup, and then each section shows you the specific parameter, which you can also manage here from this report section. So here, and in this Dropbox, you can choose which kind of sections you would like to see inside the report. So here we have head, and there are always a couple of graphs. First one is the final results, final values, and to also see the convergence, then you can see also the values for each iteration during the simulation. And this holds for any section of the report, so efficiency, for example, torque, etc. And you can also add some comparison with external data or with whatever you need. So you can edit, for example, here additional data files and to which section it should be printed. And maybe just to mention, or just to show this turbo blade to blade views. So it automatically evaluates this blade to blade view with the streamlines visualization, just to follow some kind of shape or topology of the flow in this specific view. And the same you can define for the meridional average. So this is the circumferentially averaged quantities which you choose. So here is the static pressure, and you can see the change throughout the rotor section and displayed on the meridional view. Okay, and anytime after the simulation, you can open, for example, a new render view and go to visualize the CFD results on your own. So we can click here, show CFD results. I can click on the internal mesh, so it automatically loads all the cells inside. So it loads the volume of the computational mesh with all the quantities which were evaluated. And then after the data are loaded into the GUI, you can play with the visualization. So for example, just to be curious, where the cavitation occurs, so there is a field cavitation for which you can extract the values of the threshold, the values of the cavitation. So the cavitation is a field which shows you if the cell can cavitate or not, and this is displayed by the value from 0 to 1. So 0 means there is no cavitation, and 1 there is probably cavitation in that cell occurred. So if I, for example, cut off some values close to the 0, so I can see then all the cells in which the cavitation may occur. So there is a section below the blade cap, or how to call it, below the blade, and at the leading and near the trailing edges. And you can really play to combine the visualization. So here I can go for the wireframe. Just I can set the opacity and combine the visualization of the cavitation field, for example, with the whole wireframe of the whole volume colored by the static pressure. And again, you can combine by the slice, for example. So if I set some proper slice, which could be this, for example, okay, which is not the perfect one. So let's make it perpendicular, okay. And on this, you can visualize, for example, the velocity with a streamlined tracer just to see what is happening. And again, yeah, you can play as you need to have a nice visualization to analyze the flow and possibly analyze it, see and make some conclusion and possibly updates or modification to the geometry. All right, so maybe I'm almost at the end, so I can ask Luboš if he has some comments, or if he would like to add some additional information, or what I can show in addition to this. So Luboš, are you still there?
Yeah. I'm following very carefully. Thank you, Radek. Yeah, and yeah, I like it very much. Thank you for everything. It was pretty detailed, and I like it this way. And yeah, I think that was the part. I hope that everyone from the audience understand that it's after getting some experience, it definitely does not take that much time and effort to make the setup. And definitely once you make the setup once for one kind of simulation, you can save it and then you can reuse it anytime. So you do not need to start from scratch all the time. So for example, if you have the way of preparation of your geometry developed once, and then you can just exchange the surface data, for example, of your model, and run the simulation and just generate the results. So it can be very effective and efficient after getting some experience. But in the webinar, of course, we are talking about a lot of details, and yes, there are the way more details we could talk about, but that's not necessary, I think, and it's at the end it's not possible in the webinar. Yeah, so I think it's time for the audience to ask your questions. So I would like to ask everyone. It's your time, so it's definitely makes sense if you use it to the fullest, and we'll do our best to answer what to do, how to do, what we think about what, and let's see. So maybe yeah, so maybe we can stay with the presentation on your side, Radek, because if there will be some requirements to show,
yeah, definitely,
from the graphical interface. And yeah, so again, I can't see any questions at the moment. So
neither.
Okay, so what do we do? Sometimes that we have a lot of questions. Sometimes we have, like now, we have not many of them. So what's important, and we didn't say it, is of course you can automate everything. So the simulation workflow can be anytime there are there's a lot of space for automation. It can be automated absolutely. So it can be really run on the background. You do not need to use the graphical interface at all. So it can be automated. It can be run in the batch mode, and it's really flexible. So you can use some functions and you don't use other functions. So it's really open. And I still can't see any questions. So, well, I guess we'll give it a couple of moments and then we would continue. I will take back the screen.
Okay. Sure.
And if there are no questions, we haven't prepared any questions, so maybe we should do it next time ourselves to pick some representative questions from the technical support, for example. But anyway, now it's not there. So Radek, what do you think? Do we just close the finish the
so
webinar,
we can keep it as it is. So yeah.
Okay, so let's
everyone
save.
can ask the question afterwards. Yeah.
Absolutely.
They can send us email open. And yeah.
Absolutely. So this is perhaps the first time that we don't answer questions in the webinar in like 71 webinars. Okay, that's live. So let's move a little bit. So here are a couple of those who already share our visions with us. So all of you are welcome to join us in the journey of development of specific simulation workflows. And yeah, this would be it for today. So thank you for coming.
I can see last question. So just to have really all the webinars with at least one questions, with at least one question. So there is a question from Adele. What kind of cavitation you can handle? So I will just quickly answer. If you can share my screen.
Absolutely.
Okay, I will quickly show.
Absolutely, yeah, we can see it. Yes, please.
Perfect. So this kind of cavitation we show here is just the post-processing from the steady-state simulation. So there is no specific model. It just takes the saturated water pressure, which is either automatically evaluated from the water properties, or you can add your custom value of saturated vapor pressure, and then it's kind of post-processing. So it looks for the local pressure values, and it evaluates if the pressure is below the saturated value or not, and highlight the cells, or evaluate the specific indices via kind of histogram method, which with some degree corresponds to the measurement data. Yeah, so it is the simplest model, but sometimes it can really help without enabling more detail and more demanding simulation. But for detailed cavitation treatment, you can go for the transient simulation, and within the transient simulation, it allows you to enable the multi-phase cavitation, which works on the standard Schneider-Sauer model. So you can set the parameters of the cavitation. It enables two-phase model, and it really models the cavitation as a fluid and vapor part.
Yep, this would be it. So you can go for proper cavitation, but it's of course just in the transient mode, right? But while in the steady state mode, there are a couple of options to do it, to use it as post processing, I would say.
Yes, it's just the post processing, exactly. So there is no specific detailed model, but it just follows the values which are evaluated with respect to the values of the vapor pressure. So we're just comparing the results with the possible cavitation. So it just indicates the places where cavitation occurs, but there is no specific model behind it.
Yeah, okay. So anyway, I think this would be it. So we would like to thank everyone. So feel free to come back anytime in the future, and we will gladly answer all your questions. It's our job and also a pleasure. So yeah, let's keep in touch, and this would be it for today's webinar.
Yeah, perfect.
Okay.
Thank you, and bye-bye.
Yeah, bye-bye. Yeah. Thank you. We leave you with that. Bye-bye. Thank you.